In this video, we're going to look at the average rate of change of a function. Now, this is the beginning of the explanation of where calculus actually comes in handy, but it will take us a couple of videos to get there, so just be patient, we'll get there in the end. But it's really fundamental that you understand the concept of average rate of change and then instantaneous rate of change and how that relates. So let's make a start. So the rate of change is just looking at how fast one variable changes in response to another. So a really typical example is speed, and this is usually the one we start off with. And that's where we look at where the distance travelled changes in response to the time elapsed. So you'd all be familiar with our distance time graphs. Okay, here's a really straightforward one. It's directly proportional, so we're looking at a linear relationship. It's got a constant gradient. And for this one, we're saying, well, if you travel 1 hour, then you've travelled 60 kilometres, therefore you are travelling at 60 kilometres per hour. Okay, and we know that it's 60 kilometres per hour because the gradient, or the slope of the function, is 60, and it's constant, so that's just a constant speed. So we say that when you've got a constant rate of change, then that produces a linear graph with a constant gradient. So the rate of change of a function is the gradient of that function. Now, in the real world, when we're travelling in a car, it doesn't look like a linear graph because you don't travel at a constant speed all the time. You stop and start and accelerate and decelerate. So while this theoretically could be a journey that you're travelling at 60 k's an hour, this is more like what it looks like. So you can see here we start at 0, we've got an acceleration going on, so you're increasing in your speed. At this point here, if you took the gradient of that point, it's probably close to 60 k's an hour, but then we start slowing down again, and here we flatline completely. So we've stopped, maybe sitting at lights or waiting to turn a corner or something. And then you accelerate away again, and then stop again here. So while theoretically we've travelled a kilometre in 60 seconds at 60 k's an hour, what we've actually travelled is 300 metres. So what we say is between 0 and 60, so for 0 to 60 seconds, the average speed is going to be the distance travelled, which turned out to be only 300 metres, divided by the time, which is our 60 seconds. And if you work that out, that's 5 metres per second. Or to convert to kilometres per hour, remember you can multiply by 3.6. You should know that from your physics. Okay, and that gives you 18 kilometres per hour, significantly slower than 60 k's an hour. Okay, so that's our average speed over that time. So while we don't know the car speed at any given time, we can work out the average speed over an interval, and it doesn't have to be the total interval. So if we go back here, we could say, well, what is the average speed between B and C? We can see that that's 100 metres over 30 seconds. So you can work that out. You can say, what is the average speed between A and B? So that's 100 metres as well, but that's only over 15 seconds. So you're going twice as fast. Your average speed is twice as fast here as it is here. So the way we calculate average speed is just by looking at the total distance travelled over the given interval divided by the total time taken. So it doesn't matter what the interval is. We're just looking at distance travelled divided by time taken. Now, just before we go any further, we want to clear up a little bit of terminology, because we use this when we start looking at instantaneous rate of change. So we have two things. We have a secant, which is a line that passes through 2 points. So that's the key word there. So it's infinite length, it extends infinitely in either direction. And then we have a chord, which should sound familiar from our circle measurement and trig. And a chord is a line that joins 2 points, so it has a finite length. So to illustrate, if I pick 2 points on the graph, let's say here and here, if I'm going to draw a secant through there, that's just going to be a straight line that goes through both these points. So I'm going to try and draw a straight line. Ooh, that's not very straight. Let's see. This one. So a straight line that goes through there. Okay, so that would be a secant because it goes extends in either direction. Whereas if I'm going to draw a chord, so if I pick two other points, let's say from here to here. So I'm going to draw a chord between those 2 points. That's just the straight line that joins those 2 points. And it starts and ends on the function. So this will extend and the chord doesn't. So we can put arrows on the end of that, whereas this is just finite. So just keep that terminology in mind, because we will talk about secants and chords quite a bit in the sort of next few lessons to come. Okay, so going back to our idea of average rate of change, what we're looking at is finding the gradient of the secant, so gradient of the line that goes through the endpoints of the interval. So if I wanted to say, well, what is the average rate of change of this function, which is, it's no kind of regular function, it's just sort of a random line, but I want to know what is the average rate of change between P and Q, all I need to do is find the gradient of that line. Okay, so if this is our function f of t, because we've got our variable t down here, then this value here will be f of a, because the t value there is a. This value here will be f of b. And of course, when we're finding gradient, we're looking at rise over run. So just going back to our straightforward linear equations. So rise over run, gradient. Okay, and of course the rise is the change in y. So the difference in the y values over the difference in the x values. So to work that out, we find out, well, what is the second y value? It's f of b minus f of a. And then for the x values, it's b minus a. And that's it. So we're just finding that gradient of that straight line where we've joined those. Now, obviously it's an approximation because this isn't constant. There's greater acceleration here at the end than there is at the beginning. But it would give you an approximation of the speed between those 2 points. So this is how we get average rate of change. That's why we call it average. Okay, so let's have a look at a bit of an example. So we've got a graph here. We're told that it's distance time, so we're looking for speed. And the question says find the average speed, that's your keyword, of the object over the interval from where t equals 2 up to where t equals 12. So exactly the same thing, we're looking at rise over run. Alright, so the average speed, should put average speed is going to be the change in the distance. Now it was 30 up here and 12 here. So that leaves me with 18. And the change in the time. So 12 seconds here, 2 seconds here, that means there's 10 in between. So it's 1.8 meters per second. Okay, and you get, if you plot that, you end up with a line that goes from here, straight line from here, up to there. And again, it's approximation, okay? Your acceleration, or your speed, sorry, is faster here, and then slows off a little bit, but it gives you the average approximation. Okay, so the interesting thing with average rate of change is what happens within the interval. So whatever interval you've picked, whatever happens in between there has no effect on the average rate of change. So for example, if this is P over here and this is Q, okay, and we want to find the average rate of change, so that's joining those lines. Oops, that's joining this one to here. So we're just finding this distance there and this distance here. Okay, it doesn't matter that first we've got a negative rate of change here, then it's got very steep, and then it's peaked, and now it's come back again. That doesn't concern us at all when we're talking about average rate of change. The average rate of change is still this distance here, this difference there, and the difference there. So all this stuff, whatever goes on in between, doesn't make any difference. So what that means, when we get given something like this example, where we've been given a function and we can see that's a parabola, which means there's a turning point in there somewhere. We're not interested in whether that turning point falls within that interval. It doesn't make any difference. Okay, so all we want to know is we want to use our formula, which is our average speed or average, you should put rate of change because this one isn't necessarily speed. So the average rate of change, and remembering from our formula was the function value at b minus the value of the function at a over b minus a. Now in this case, the interval given is 5 to 1 over 5 minus 1, and if you work that out, which I will leave you to do, you should get 20 minus 4 over 5 minus 1, which will give you 16. Okay, we haven't been given any units, so it's just 16 units as a rate of change. Okay, so we're not concerned with what's happening in between. It doesn't matter if it goes down, if there's a turning point. All we want to know is what's happening at the beginning, what's happening at the end, what is the difference between those, and that gives us our rate of change, average rate of change. So, in summary, the rate of change of a function is the gradient of that function. When you've got a varying function, then obviously the gradient varies all the time. Okay, a constant rate of change will produce a linear graph. That's where you start getting your straight lines. A secant goes through 2 points while a chord joins the 2 points. And the average rate of change is given by this formula, and that's over the interval AB. So whatever you define your interval as, that's how you can work out the average rate of change between those 2 points.